Here's a quick introduction to our project, Railway Anomaly Detection System, or RADS for short. What we intend to do is perform anomaly detection on video streams of railway tracks. So this could potentially help in averting anomalous events such as people or animals crossing the track, or events such as a car breaking down on the track. A naive approach to solving the problem would be to look at all the possible anomalies in the case. For example, that could be people crossing the tracks, animals, or vehicles, but that would just be too many cases to model. Instead, we turn the problem around where we model what is not an anomaly. In this case, a normal situation would just be empty tracks or tracks with trains passing by. And we exploit the dataset to overfit the autoencoder on the training dataset. And this turns the problem into an unsupervised learning problem. Here's an overview of the data processing pipeline we have. This is what the raw images look like, captured from the Arduino. As we can see, the images are not still and not aligned. So since we are interested in detecting anomalies on the track, we would like to focus on the relevant regions rather than the whole image. So we try to transform each image so that we just end up with relevant portions of images like these. And the way we do that is create a mask, use edge detection and huff transforms to detect horizontal and vertical lines in the image, and then solve the intersection points, and that would give us a mask which we would then apply on the image, and then we would have to rescale the image so that it's compatible with the embedding model. And here's the Python code that does that. So we would read a specific image from our dataset, obtain the feature vector by first transforming it, we do a edge detection and then perform the huff transforms to get the orientation of the lines, solve the intersection, and build a mask, which would then be used to mask our original image. And we then have a image just as a tensor or a numpy array. So the result would be something like this, where we have nice segmentations of the tracks rather than the region surrounding it.
Now let's get into the image embedding model. Our custom-made image embedding model is based off the pre-trained model MobileNet v3. In fact, it is, as mentioned before, a pruned-down version of the MobileNet v3 small pre-trained model. The reason we needed to prune it down is due to the inherent hardware limitations in the Arduino itself. MobileNet requires over 80 MB of RAM, and we were only provided with 256 KB of RAM. The entire MobileNet model, which was not possible, was then sheared down to only consider 2 of the 12 convolutional layers within it. And after shearing it down, while it did possess enough parameters to fit within the limitation technically, the added complexity from layers like add and relu, which do not really include parameters, still strained on the RAM of the Arduino, causing it to require over 12 MB of RAM to process this sheared down version. So in response, we decided to customize this further by creating our own unique blocks to imitate the MobileNet version, and then we can customize the number of filters we want and take out some of these unnecessary, well, it was necessary for MobileNet, but unnecessary for us added complexity like this add and padding here. To do this, we created a custom squeeze and excite block. This imitates this block right here, which follows any kind of convolution with an internal convolution and dense layers within them, and then multiplies the initial input. So it brings a relation from the initial input to the output of the other branch. Over here, instead of having multiple convolutions within the squeeze and excite block, we used dense layers. And the reason for this is because they simply did more with less parameters. And it's what worked best for us. So the model that we are looking at here after customization looked somewhat like our working model here. And even after customization, we found out that there were too many layers, which we then pruned down even further to this final model here, which is the model we currently run on our Arduino locally on the computer using Python on a dataset called RailSem19, which is an open source dataset for semantic railway segmentation. After we've got our model, we then converted it to a TF-Lite file, and also we had to ensure that the inputs of the file were of type int8. The reason because that the data type int8 takes much less space than float32, which would then allow us for a larger model. After which the model was converted into an h5 file as well, which was done in the function above. Over here. This model was then taken into our Arduino, and within the Arduino, the process from the Arduino is quite similar to Lab 3, where we just declare a tensor arena. Perhaps the only difference is that we had to declare input-output tensors and also include the data being fed in directly from the camera. Of course, we also had to initialize the camera and ensure that it works as well. And I guess that concludes our introduction to the image embedding model.
So we have an elegant neural network implementation from scratch with the following layers implemented. That would be the linear, ReLU, and squared loss, supporting both forward and backward propagation. In the forward propagation, we would go from the left to the right, where each layer would receive the output of the previous layer. And in the backward propagation, we would propagate the gradients from the right to the left using chain rule. So basically, it would be calculating the downstream gradients as a product of the upstream gradients and the local gradients. That is, dl dx would be dl dy times dy dx. And to help alleviate some of the convergence issues, we also run a momentum stochastic gradient descent algorithm. So here are the mathematical equations. The linear layer would involve computing wx plus b, and the backward would be the derivative of the loss with respect to the input. And we also have the gradients for the weights. ReLU is just max of 0, x, and the backward would be the upstream gradients times the local gradient. And we use the squared loss as the loss function, which is just the squared L2 norm of the true labels and the predictions. And the gradients is just the y minus y hat. So we use the use these layers as building blocks to build up an autoencoder of a structure like this, where the first layer here is the input layer, which would be the embeddings, followed by the linear layer comprising of 10 units, and then a second hidden layer, then the third and the last hidden layer, which matches the size of the inputs. So here's the overview of the code. So this class implements the linear layer, which has the input size, the output size, and the batch size, and weights and biases. And we also keep track of the last input for the back propagation. So we initialize the weights randomly using a uniform initializer, which is just sampling between the interval of -1 and 1. And here are the forward implementation, which would be similar to this, the backward, and the gradients of the weights and the bias. Similarly, there's the ReLU layer, which is not a trainable one, but it just activates the inputs. So the forward is just the max of 0, x, and the backward would be the upstream gradients times the local gradients. Yeah, and that involves an element-wise multiplication. Then there's the squared loss function. So that's the sum of this squared error, y hat minus y squared, and that's the derivative. And then we would network. Then we would first we would initialize all the hidden outputs. That would be the matrices here, H1, H2, H3, and H4. The upstream gradients, matrices to all the upstream gradients, the downstream gradients, and the gradients of the weights. Then we would move on to the training function down below, where we would iterate over the epochs, and for each batch we would receive a batch through the serial, which would be a embedding, and perform the forward and backward propagation. Forward would involve feeding the input through all the layers, and then the backward would involve computing the gradients and propagating them back. So the first upstream gradient would be derived from the loss function, which would then be the input to the last layer, and then there is the momentum gradient descent, which is just the where we add up the negative, move along the negative direction of the gradient, and multiply the gradients by the learning rate, and we just do that in the reverse order, and that would be the loss, the reconstruction loss. Yeah, that would be a training epoch on a run on an Arduino, and in case of distributed learning, each agent would be trained on a subset of the data, and then between the epochs we would do some sort of weight synchronization, which would be just averaging the weights, and we would just repeat the process. And here are some of the hyperparameters for the training. We have a batch size of 2. That's the most we could fit on device at a time. There's the momentum factor and the learning rate.
Is part of the code that constitutes the platform. That is the base software layer that manages our Arduino devices, and on top of which we build the more complex functionality of our project, such as, for example, distributed learning, image acquisition, and embedding. The platform has a few key roles in our project. First of all, it runs the state machine of the device. Our Arduinos have to comply with a multitude of tasks, which need to be coordinated in order to run the entire operation smoothly. An example is coordinating with each other to perform distributed learning, as well as receive the embeddings from the image acquisition device. But the devices also need to be able to communicate with the client, accept its commands, and answer them in a timely fashion. Implements the serial communication with the client, which is key in transmitting the large amounts of data that we need to move around in our network to perform correctly the tasks that it needs to complete. Part of these communication requirements, we also implemented in the platform the Arduino side of our custom communication protocol that we made from scratch specifically for this project. This protocol, of course, takes into account the key needs of our platform and of our project. While designing the platform, we took great care in making sure that the code that we wrote was general enough to allow us to expand it in the future with minimal effort.
Hi, I will be explaining Bluetooth Low Energy for the IoT project. Basically, we have two roles, peripheral and central. In the left, the peripheral, in the right, the central. The peripheral is responsible of advertising with a UID, the identifier of the device, and that service set characteristics. They can be read, write characteristics, indicate or notify. That just limits what the central can do or cannot do. And then I will go also to the loops of the protocol. This is how you will understand how it works. So check out the flag that we have here. So this flag is when the central has written, it will be one, and this flag is when the peripheral has written. And you can see here in this sketch overall how it works the protocol. So you can see it has a server of laptops and devices that are separated through a network that is wireless. So we have the data set, we are training, we updated the weights in training, and then we share them in batches. And then after sending them all the weights and devices, we keep training again and again and again. And that's how the distributed learning works. So something really important before going up in the handshake is here that we have the number of weights of 25 in both devices, or weights of floats. So multiplying that by 4, you have 100 bytes. If you go to the documentation of the Arduino, the limit is around 500. In this case, we were not able to send 500 bytes from just one time. It was degrading the communication. It was having some troubles on us. So that's why we set this number to 25 when we know it is safe to do the protocol. But you can test that in your project. Now, going back to the loops, this is how the loops work. So we have a peripheral and central. The peripheral send the weights. The central receive these weights and average them with these internal ones. It sends back the peripheral stores it in memory, and then he updates something called, we have row and call index, so the new batch can be sent to the central, and so on. It keeps going over and over. So basically, the central is responsible of averaging the weights, and the peripheral is sending to update the row and call index, or the batch order. So we have the flags here. I receive a flag from the peripheral that that flag is on. I receive, I average, I send back, and then I receive, update, and then send a new batch, updating the parameters. I will go through the functions so you can see that here. So just the peripheral has this code to update the row index and call index. And you can see if I go to receive, is mostly the same. Now, let's go to the flags briefly. We have mostly three flags in the code. We have the sync flag. This is a flag that we set at the beginning when the central is looking for the peripheral. So it keeps sending this blind packet. So this flag can be turned on and it can keep in the loop here. And then the communication protocol starts. Second, we have a bias flag. The point of that is that we have two matrices, one of weights and another of biases, of course. And when we finish sending the weights, we turn this flag out and then we send the biases. The thing is that the matrix of the biases, it has just columns. We don't care about the row index, and that's why we uh, we put this flag in the code. Finally, we have the stop flag, and which shows us the when you are able to train again. So we finish sending all the weights and biases, you turn this flag off, you train, you turn it off, and then you can send again. Finally, I will go through the functions, the one of the functions, for example, of the send weights in batch. So this is where we copy from memory what we are going to send in the buffer, and then we write the value to the other Arduino. And this is how it works. The switch and case, the layer index is just we have 4 layers in the route encoder, and that's why we have this switch